started my own business in October of 2010, and it wasn't long after that that I was trying to dive into the importance of mycorrhizae.
Yep.
And I had used some before from another company, just those little tea bags, and didn't have much of an effect. But I knew that there was promise. So I started searching online for mycorrhizae, reading about it, and I ran across this company called Mycorrhizal Applications.
Right.
And they seemed to be the best. They seemed to know what they were doing. So I called them directly, got a receptionist, and started asking questions. And finally, she said, "Well, you can get this product from 3 different people in California." And she named NRG and John Andreas, and she named 2 others. And I said, "Well, okay, I need to pick one. Which one would you pick if I was going to pick one that would steward the product best?" And she said, "Without a doubt, Mr. John Andreas." And so I called John.
Because of me, that was us. So okay. But anyway, yeah. And so then we met up at like the Almond Board conference,
Yes.
I believe, right after
Yeah.
that.
Well, actually, I think we met out at a growers out in Vernalis, California, and gave a presentation. You and Kai
And did the presentation.
Yep.
Anyway, been around a long time, so I've taught him a few things. You've taught me an awful lot, and that's why he's here today. He is going to talk about nitrogen fixing endophytes, and it's a specific product. And so a year ago, we were at the ValleyAg conference, and we were talking about Dr. White's presentation and things, and he said, "You know what? I've run into this product." And so we've been doing some work with it, and he's going to share a little bit about this. I think you'll be fascinated. Goes really well with what you've already shown us, Dr. White. The power of microbiology.
Is this the right clicker, or is it which one?
The other one.
Or is it, oh, there it is. There we go. Yeah, nice. We can.
Yep.
So advance.
Down button is
Advance.
advancing, and
This is the
green
pointer.
is your pointer.
Great. Well, thank you. So again, my name is Tracy Miller. I'll just want to give you just a tiny bit of background about myself, so you kind of understand where I'm coming from. I grew up in agriculture up on the east side of Modesto and in the little town of Houston. My family was primarily into growing clean peaches for Tri-Valley growers. So maybe some of you know about that company and all the turmoil that went down with it and all the lost retained earnings that growers lost over it, but bad deal. But anyway, we grew a lot of crops besides just peaches, a lot of nuts, a lot of annual crops. And so I was raised in very, very strong conventional chemical agriculture. That's what I grew up in. And went to college here at Fresno State, got my PCA license shortly after, went to work for a independent ag chem fertilizer business, selling chemicals, walking fields, just like a regular PCA would do. Got my CCA license as well soon after. So that was about 26 years ago, roughly. And I liked being a PCA. Actually, I enjoyed it. You know, you could find a problem, you find a solution, make a recommendation, sprays are applied, problems are solved. And I started noticing probably around 2010 that things just weren't working anymore the way that they had. And the last 5 years is even much more so. And I had a friend that probably around 2007, 8, he was up in Yakima, Washington, started throwing ideas out at me that I'd never heard. Started saying, "Hey, you ever heard of John Kempf?" Things like that. And probably around 2010, he says, "Hey, you ever heard of Acres USA magazine?" No. He says, you ought to subscribe to it. Well, by chance, I got a postcard in the mail not long after that, and it sat in my desk for 5 years. And I would open that, and I would see it, and I thought, yeah, I ought to subscribe. Well, I finally subscribed in 2015, and I said, you know, I need to subscribe so that when I confront one of these wackos, I can refute them. I have an argument, you know, to be able to tell them why it's just hippie culture trying to teach us all how to farm in a hippie way. And so at that point in time, I had known John Kemp. I had read some of his things, and so I subscribed, and I get my first magazine, and I open this up, and there's this huge ad there about from Advancing Eco Ag, and I'm going, John Kemp is in here, and I started reading articles, and I'm like, well, that makes sense, and that makes sense, and that makes sense, and it has started to open up a whole new world for me. And I'll just share that in 2017, I was introduced to this product called Twin N. And at that time, I was working as an agronomist for Mid-Valley Agricultural Services up in the Linden area. And we were continually having people come to us with the latest and greatest product. And so I got a call one day from this man, and he says, hey, I got this product that I think you'd be interested in about and known about. Well, the referral happened to come from my friend in Yakima, so I felt like, well, I got to give this guy the time of day. And he started telling me about this product, and I'll come back to this in a moment, but I was ready to chuck this product out the door and say, that is too good to be true. There's no way. And so I'll get back to that story here in a moment. So anyway, our talk today is harnessing atmospheric nitrogen through the use of endophytes. I was thinking that it was going to be a real tough act to follow Dr. White, but I'm really glad he went before me because he explained a lot of things that I don't have to explain now. So let's jump into it. So we have a couple questions that we would like to ponder today, and I sense that we have a very smart crowd here, and this is you've asked a lot of good questions, so I'm sure you'll know all of the answers. So first question. Our atmosphere contains 21% oxygen. It also contains roughly 0.04% carbon dioxide. How much nitrogen gas in percent is in our atmosphere? Anybody, just shout it out. 78. That's what I'm hearing. Great answer. So if we have 78% nitrogen gas in the atmosphere, then does anybody know approximately how many tons of nitrogen that would translate out that is hanging over the top of every acre of ground? Any guesses? Every acre of ground has how many tons of nitrogen gas sitting right on the top of it? 100 tons. You're a long ways off. What was the other number? How many?
1 trillion tons.
Oh, no, you're too high. So 34,000 tons of nitrogen is hanging over every acre of ground. I'm sure it's an approximate number. And so the question then, given that we've got 34,000 tons of nitrogen gas sitting over every acre of ground, how come so often if we don't add nitrogen to our crops, they go nitrogen deficient? Why is that? Oop, I keep pushing the wrong button. The question is, number one, why is it? And number two is, can we access this nitrogen? And if we can, how do we access that nitrogen? Is it even possible to access that nitrogen? The thing I would just say is, how have the forest over the millennia got their nitrogen fertilizer? And so that's just a thought question. So the difficulty with atmospheric nitrogen is it is two nitrogen molecules that are held very, very tightly together by a triple bond. That triple bond is a very, very stable, or it makes a very stable form of this nitrogen as a gaseous form, and it's hard to break that bond. And there's good reason for that. If that bond was easy to break, and the oxygen that's in the atmosphere could then attach itself to that nitrogen, we'd be forming nitric oxide and nitrogen dioxide, both of which in high amounts can become toxic, would cause major pollution and so forth across the world if that was possible. So it's good that that nitrogen gas is stable, but it also means it's very difficult to access. So there's really three ways known by which nitrogen gas can be extracted out of the atmosphere. This first method, and I'm going to start from the left, is the whole process of industrial fixation of nitrogen. And this is what happens when a fertilizer company has figured out how to take nitrogen gas out of the air and synthesize it into a liquid or into a prill or however it is. It's through this fixation process. And this is what we call the Haber-Bosch process. And there's actually a couple other people that had figured out different ways, but the main popular one is the Haber-Bosch process, and I'll show you that in a moment. Then there is fixation that occurs every time you have a thunderstorm and you have a lightning bolt that strikes across the sky. There is a splitting of that molecule of nitrogen in which it can become available. And then there's biological fixation, which Dr. White referred to. And so I'm going to jump into each one of these just in a little bit greater detail to help you kind of understand what's going on. So this is industrial fixation. This is what is happening when a large manufacturer, say for example, say Simplot or whoever it might be that is making nitrogen fertilizer. What they're going to do is they're going to take pure nitrogen and then they're going to react it with hydrogen that's coming from natural gas. So it's a very, very high energy input that is going into making this nitrogen. So in the process of this reaction with natural gas, nitrogen, hydrogen coming into a reaction chamber, there's a ratio roughly of 1 part nitrogen to 3 parts hydrogen, and it's done under extreme heat, so 400 to 500 degrees Fahrenheit, roughly 45 degrees Celsius, and 200 atmospheres of pressure, so intense pressure. And then they have an iron catalyst that they use, and then after they heat that up under tremendous pressure, everything's cooled. And then what is able to come out, they're able to extract ammonia as liquid ammonia. And it's from there, from liquid ammonia, that then all the other types of nitrogen-based fertilizers that we use that are synthetic are made. So basically, you know, here's your liquid gas or your liquid ammonia. And so it's from there that it goes on. So that's the industrial process. Very high energy input, essentially a very high carbon footprint that is taking place for the manufacture of that fertilizer. So the next one is atmospheric nitrogen, is atmospheric fixation by lightning, which we don't have a lot here. If you're living in the Midwest and you see a lot of lightning storms, you're going to see this much more frequently. But this is the process by which when that lightning bolt strikes through the air and there's a splitting, and I'm not sure I can even explain it, but these two nitrogen molecules bound together by a triple bond are broken apart. And as soon as that happens, oxygen is allowed to be attached as nitrogen dioxide. And then these oxides then dissolve in the rain, and then the rain that comes rains down nitrogen. So if any of you have ever grown a crop where you had a big thunderstorm, maybe you got an inch or so of rain after that thunderstorm, it's during the growing season, you'll often see a green up response after a storm like that. And you can get 50 pounds of nitrogen from an average lightning storm. So it's kind of a neat way to get some free fertilizer, but it's not something we can depend on at all here in California. So that's kind of what's taken place. And I don't know where this number exactly came from, but someone said that that's 5 to 8% of the fixation that takes place. The one that we really want to talk about today is biological fixation, and I don't really want to focus on the fixation by rhizobia bacteria, that form the nodules on the plant roots, but that's what most people think. When they think of fixation, they think right to rhizobium bacteria. But we're going to expand beyond that. But essentially, what nitrogen-fixing microbes do is they have to have the presence of an enzyme called nitrogenase. And that enzyme requires two nutrient components in it that are important to remember. So iron is one, molybdenum is another. I think Jenny mentioned iron earlier being tied up by glyphosate. True. So a lot of glyphosate in a soil system or in a cropping system is going to potentially impact the ability of the nitrogenase enzyme to be developed. The other thing that I like to stress, anybody that is using nitrogen fixing organisms, there will be times where people put them out and they're like, man, well, they work great, fantastic. And other times they didn't work at all. It's not necessarily the fault of the microbial product. If that soil does not contain sufficient molybdenum, that microbe will never be able to utilize nitrogenase enzyme, and it's never going to be able to capture that nitrogen gas. So always, always, always make sure you're incorporating some molybdenum fertilizer in with applications of your microbes that are nitrogen fixers. That's a key point to making it work. So anyway, they in the presence of this enzyme, they are able to capture nitrogen gas that comes out of the air and to fix it into a usable form and ammonia for the plant. Now, one thing I want to say specifically about soil-dwelling nitrogen fixers like rhizobia is they really need to be able to extract the nitrogen gas that is in the pore space within that soil. So think about if you have a very compacted soil that does not have adequate pore space, how much air can you expect to be driven into that soil, and how much gas, nitrogen gas from that air, can you expect to actually be there for them to capture? Probably not much. So if you're out putting, if you've been farming conventionally, you got pretty hard compacted soils, or if you're a grower that's putting pre-emergent from tree trunk to tree trunk, sterile orchard floor, that is a setting for absolute failure of these types of microbes every single time. Because if you can't get air into your soil, they're not going to be able to breathe, for one. And number two, they're not going to be able to access any of the nitrogen gas that's in the air that's getting pushed into the air, into the soil by the air. So that's just something to keep in mind. But our talk is really more than microbial, or excuse me, than rhizobia bacteria. We want to look at some of the others as well. So all of these microbes that fix nitrogen gas are collectively called diazotrophs. And Dr. White actually had one of his slides that said that these are diazotrophs. And so these include rhizobia. There's also two other bacteria that I found that are nodule forming nitrogen fixers. They are this, I just went backwards. This Frankia genus, it's a symbiotic bacteria that forms with a plant that's similar to legumes, but it's a nodule former. And then there's a cyanobacter that is symbiotic with lichens and liverworts and ferns and a cycad plant. Then there are these free-living bacteria. They can be non-symbiotic in the sense that they can dwell in the soil on their own and still have that ability to fix nitrogen, but they can be symbiotic as well. And there's a whole list of them I just found that I put up here. The bottom three are highlighted because those are the organisms that I want to talk about today. So these are what I'm going to call three higher performing diazotrophs. This first one is, I'm just going to read the genus, Azorhizobium, and this is a free-living, symbiotic-forming, endophytic nitrogen fixer that can establish itself both on roots. It can actually establish itself on stems. I read that, if I understand, they can almost form it's like a little nodule. They didn't call it a nodule, but it's like a little, kind of a little bump on a stem of a plant, and they can fix nitrogen gas there, or they can go to other tissues within the plant. And this is on both legumes and non-legume plants. The other species is Azoarchus, and this is a free-living nitrogen fixer that lives primarily as an endophyte throughout the tissues of the plant. And then this last one, Azospirillum, is a free-living nitrogen fixer that primarily dwells in the rhizosphere around the root, but it can go into the tissues as well. So all of these three diazotrophs are available in this product called Twin N that I'm going to talk with you about today. So the next slide that I want to kind of, well, maybe I'm jumping ahead of myself. Let me just explain a little bit about what it is. It is a biological product that has plenty of evidence out there for increasing yields, reducing fertilizer inputs. The company that manufactures it is Mapleton Agri-Biotech out of Australia. They've been making this product since 2002. So they've got about 22 years now in production and in research. So it's kind of interesting. I was talking to somebody recently, and maybe I don't know if I should share or not share who it was, but it was Mr. Tuttle up at Farm Grade in Idaho, and he was telling me about their work with nitrogen fixers, and he made this comment. He said, "My father considers Mapleton Agri-Biotech to be the standard when it comes to nitrogen fixing microbes." And I thought, now that's very interesting, because I think a lot of them, I think they're doing good things, but for his father, I think is it Kelly? I forget what his father's name is. Kelly's the father. Yeah, I think he said Kelly is the one that said that. And so that was about, actually that was earlier this year. I met him for breakfast, and he shared that with me, and I thought, well, that's a good confirmation that we're maybe working with something good. But anyway, it's a freeze-dried product. This picture here is actually the little vial that it comes in, and the amount that you put out is very, very tiny. It's so tiny that you're like, there's no way possible this could work. But again, this is my suspicions when I first received a package, and I said, that's what I'm supposed to put out? Really? But anyway, it is made in a modern facility, and they have very high level of quality control there. The concentration, so there is 75 billion colony forming units per gram, and you only apply 0.2 grams per acre per application. So you're putting out about 15 billion colony forming units is roughly what it comes out to. If you store it in the refrigerator, which is where it should be stored, it usually has about an 18-month shelf life, and in the West here, it's primarily being sold in 12.5 acre package sizes. So that's just some raw basics of the product. But I want to kind of talk about how it works.
Just to give you a visual.
Visual aids are good.
12.5 acres worth of material.
Yeah. So what I'd like to do, I want to show you or explain this first mechanism by which it works, and then I'm going to go back to my opening story. So basically what's happening is there's three mechanisms by which this product works. The first is the nitrogen fixing component that I'm going to show you, that's all on this slide. And basically what my first little point there is saying is that once it's applied into the soil, these microbes will quickly colonize the root system. And what I'm more referring to is so you have these that are more of your rhizosphere dwellers that will colonize right on the surface of the root hairs. And then that's where they will dwell, and that's where they'll kind of do their thing. And so they are trying to capture that air, the atmospheric air that's getting pushed into the soil, and fix it into ammonia where the plant then can absorb it through the root system. And I wanted to kind of just mention, I don't know if any of you ever thought about it, but there's high pressure weather systems, there's low pressure weather systems. It's the high pressure weather system that actually has a downward effect on pushing air to the ground. So when we're in a warm weather or a high pressure system, that's when air is getting pushed in. In a cold weather system, air is actually rising. So that's where it's kind of more coming out of the soil. But you've got to have kind of more high pressure systems. You've got to have a porous soil for this air to get in. The second point, or the second aspect of the microbes, is you get this other group of microbes that come in contact with the root after colonization, and then they are being taken up by these root hairs and then mobilized up into the leaves and into the branches. And so this is what was being presented to me on the phone one day, that these microbes are applied to the soil, they're watered in, they are taken up by they're colonizing the root system, they're being taken up by the root, and then they are mobilized through the vascular system into the foliage. And then when the leaf is undergoing photosynthesis and taking in carbon dioxide, through that process, these microbes are right there sitting around around the stomata, and they are grabbing the nitrogen gas that's in that air, and then they are fixing it into ammonia. And that's when I was just, it was a stretch of my mind to accept that that could be true. And I just remember shaking my head, and after I got off the phone, he sent me a little PowerPoint, and I looked at it, and I was just like, and he was requesting that I do a trial. And so this was on my mind, do I really want to invest time in this? And so at that time, I had a 45-minute drive home. I remember driving home that evening. I was probably 10 minutes away from work and driving down Jacktone Road, heading towards Ripon. And I remember just looking out and seeing the fields. And it was like God was starting to ask me questions. And he said, how much nitrogen gas do you think is in the atmosphere? Well, I knew that question. I knew that answer. It's like 78%. Why do you think I put it there? Is it just chance? Does God do anything for chance? He didn't do anything for chance. Everything has a reason. Even our appendix that they think is just a leftover body part. It's not. And so then it was like, the next question was, hey, those green forests that you like to see and go up into and fish and hunt and all that, who's been fertilizing those for the last how many eons? Have you been watching, manure trucks driving all over spreading manure and compost? Who's been fertilizing them? And all of a sudden it was just like, I just felt like it was bam. I was put in my place, I guess I would say. And it was right at that moment that I realized that, you know what, maybe there is something to this possibility of microbes living within plants and doing these things. I had already understood that our microbes lived in our gut. So I was like, well, why wouldn't they live in plants? That doesn't seem too complex. And so it was by this process then that my mind kind of started opening up to this idea. So essentially the last point here is, for the benefit of providing nitrogen to the plant, essentially what the plant will do is the microbes that are dwelling inside of it as endophytes, they will give it carbohydrates, sugars, nutrients for their sustenance. I thought it was really interesting what Dr. White said, how microbes will lose their cell walls, and then at a point in time they get ejected, gain their cell walls, pick up some more nutrients, go back in. So that's very well possibly happening here. I'm not sure that we know whether that has happened or not happening, but it could be. The microbes that are dwelling in the rhizosphere on the outside of the root, of course, are being fed those carbohydrates, sugars, all those through root exudates. And so that's essentially what we have going on here with these root exudates coming out and then feeding these microbes. So that's the first mechanism. The second mechanism is basically, it's an effect that Dr. White has already talked about. These hormones, or these three nitrogen fixers that are in twin N, they know for sure that they are actually producing auxin hormones around the root hairs, and maybe inside even the root hairs. And it's providing an elongation of the root system. And so one thing that's being observed in the research is a much larger root mass from these microbes. And one thing that's real fascinating is as the root system expands, you have greater nutrient efficiency as far as the uptake of applied nutrition. And not only that, there was some trial work that Dr. David Holden did down in, I think he's in Oxnard, I believe. But David, I don't know if any of you know who he is. He's probably one of the foremost researchers in California in ag. Does very, very high quality work. But he actually did a leaching study with Twin N to see if Twin N could impact or reduce the amount of nitrate lost through leaching. And I don't share that presentation or that research, but that research is available, and it's really neat how the loss of nitrate out of the soil system was reduced simply with the use of Twin N. So, and they think the function is essentially growing a big root system. So that is the first or the second mechanism. The third mechanism is basically this improved plant health and improved soil health, which Dr. White talked about, how these microbes tend to provide almost a defense mechanism or increase the resilience. It's known that there is a number of trials where Twin N has reduced fusarium, it's reduced various other root diseases, Pythium, I believe. So there's this other side benefits that they're seeing happening. So that's some of the mechanisms. So basically, what are the benefits? I just kind of listed a big source. Some of these or a list here. Some of these we've already gone through. But basically, you have access to atmospheric N. You have an increase in your root mass. All of these things are leading to greater use efficiency of nutrition, better water use efficiency. So you can kind of read the list that I've put down there. So we'll move on to some trial work. This first couple slides is some trial work that I actually did when I was with ValleyAg on some organic amines. And so this was a 3-year trial. Over here on the right side of the slide, I have the actual July leaf nitrogen values. That was an average. We pulled, dozens of leaf samples. We were sampling 4 different spots within each treatment within a field. So it was a 35-acre field that was split right in half, had 2 irrigation sets. The grower that we were using it on said, yes, I'll let you do this trial, but you have to put the Twin N on the worst side of my field that doesn't perform very well. Because he said, if you can bring the yield up to match the other side of the field, I'll believe it worked. So it was really exciting when we did this work, and we ended up getting on the non-pearl variety 588 pounds per acre increase over the control. And then in the Aldrich, we had 571. In the Monterey, we had 266. And that probably was because prior to this, we had actually a quite heavy crop one year, and I think it affected the return bloom. So that was some initial work that was done. We also did another one on a 17-year-old organic block that was nearby. This one was just a 1-year trial, and we still saw, even with a 1-year trial, and this actually only had 1 application, and I'll get to some of those applications in a moment, but we had a 466-pound increase on the non-pearl, 233 on the Monterey. If any of you know Bharat Basabri with Basabri Ag Research, he used to be a senior research scientist with Dow. He developed and really helped develop Lorsban and Success, those products. He did a trial on some 8-year-old Independence almonds, and I will say one thing. So this is 1 year, and he started his first application, did not go on until May. You're supposed to put the first application on generally the middle of February to the 1st of March. He didn't apply till the 1st of May. I couldn't believe it worked, but he still got results. 236 pounds on the trial where he was using 75% in, and then 131 pounds where he was using 100% of the nitrogen versus the control. I'm going to show you some work that was done by Dr. David Holden. This is in strawberries. This is showing the flats per acre where he used Twin N versus where he didn't. And basically what he did is he had a full 100% nitrogen program with CAN 17, and then he looked at applying only 75% of the grower standard nitrogen, and he did 4 applications of Twin N. So this is the first time I had ever seen a 4 application use of Twin N, and he got 528 flats of strawberries per acre versus 4,000. Excuse me, it was 5,208 versus 4,661, and then that translated into a dollar revenue of $4,483 per acre profit, which was, this is probably the most incredible research I've ever seen on Twin N. Usually it's not this fantastic, but this was pretty interesting to see. Then he did some work with lettuce, and essentially what he did was he had a grower standard treatment. Treatment 2 was grower standard plus Twin N. And what I'll tell you is when you run full nitrogen and you add Twin N to it, you usually don't see much benefit. His third treatment was 75% of grower standard nitrogen with Twin N, and then fourth treatment was no Twin N, but at 75%. And so the results that he ended up showing was, so here's treatment 1, full N. Let's just look at boxes per acre of lettuce, 529. If you take full amount of N with, full amount of nitrogen with Twin N, 537. So he only got a 1.4% increase. And then treatment 3 was he cut his nitrogen by 25%, added Twin N, he got 582 boxes per acre. And so essentially that translated for him, I thought I had the note in the profit, but yeah, it was a 10% increase in both yield and profit with a 25% cut in N along with the Twin N applications. He did the same thing on broccoli, same exact strategy of program, full in with Twin N, 75% in with Twin N, and 75% in is what he did. And then essentially here's his results. So yield per acre, standard was 734. He actually went down a little bit with the full in with Twin N. But when he cut the nitrogen by 25% and added 1 Twin N application, his boxes per acre went up to 805. And that's compared to a 25% reduction in N without Twin N at 552. So it seems like there's a real nice benefit when you cut your nitrogen levels by at least 25%. If you are interested in any other research, you can go to this website, dohops.com, and Doug Whitener is the owner of that website. He's the sole distributor currently of Twin N in the U.S., and he has a lot of this research posted. I also have a lot of other additional research posted, but there's a lot of trial work on many other crops. Do I have?
Happy to share with you.
He will be very happy to share, and
You ask, he will inundate.
He will. I have a lot of other research papers he's given me that are not posted right now. So I don't know if you want me to go into best use, if we have time for that. I think this is my last slide, or whether you want me to keep going. Okay, we'll go real quick. So the rate is 0.2 grams per acre. Usually we're looking at least 2 apps, especially in tree crops. I'm currently doing 2.5 apps where I do 2 spring applications in trees, and then I do a half app application, half rate in the fall. But 0.2 grams is the going rate. Always apply it with water in some way. So it could be injected with knives, but usually through the sprinklers is the way you want to deliver it. You could spray it right on the ground if you had a heavy rain coming immediately, but you don't want to allow it to sit. No chlorinated water. Don't mix it with anything. They don't want to mix with fertilizers, chemicals, etc., because of the salts. I'll be right. Water pH, you probably don't want it very acidic, and you probably don't want it super alkaline. So that's a good question. I don't have the answer to that, but if you are sitting at 9, I would probably add a citric acid, organic-based acidifier. Apply it early. Dr. White mentioned how these microbes colonize early in the growing season. I think that's a very vital point, that applying late, you're going to get less results, just like Bharat Basabri. He still got results, but he lost a lot of the potential. How much can you cut back? I would start with 20-25%, get comfortable with the product, and then go maybe down to 40% or so. I believe that a single application of Twin N can give us close to 50 units, 40 to 50. That's what my experience has showed. 2 apps, I think I'm getting 80 to 100 roughly. You can use, I'd say, 1 to 4 applications per year. And if you want more information, you can contact John, Kai, myself. Go to this website, and I would be glad to share more. I'll be around for questions. Thank you.